So, if you recall when we did RNN, one of the major bottlenecks for RNN, even if you do the LSTM or GRUs kind of framework, is the fact that if I am looking at the encoder, right. So, this is the encoder, right. What do? I have to feed one input, let us say at time instant t minus 1. This passes through this entire, this is the hidden layer, right. And then the output is actually fed back along with xt here, right, and this is the output st, right. So, this st is going to be multiplied. So, I at this point sorry, this is st minus 1. Okay. So, at this point I need two inputs, I need xt, but I can't feed xt without getting st minus 1, right. So, I have to process st minus 1, get the output before I feed it to the encoder. Then at this output I will get st, which again will get fed back, along with it I will feed xt plus 1, right. So, at xt plus 1 I cannot feed xt plus 1 independently, I need xt plus 1 and st, right. So, I not only need xt plus 1, I always have to wait for the previous guy st, right. So, when I am looking at x4, I have to finish x0, x1, x2, x3 before I can handle the S4 entry. So, if I am looking at I am or how are you, right, for RNN I have to first feed this embedding, right, then the output will come from there and then it will come here, then output will come from there and come here. So, I have to wait when I want to feed in U, I have to wait for how to finish its processing, R to finish its processing. We are going to feed them through vectors like one hot or embedding, and then only U can be processed. So, this is all going to be done by the encoder, right. Similarly, the decoder, right. So, each one of these are going to be taking a lot of time because of the sequential nature. So, we want to parallelize things, right. And last class I had talked about one way to parallelize, which is a very useful thing, right. So, which is to use convolutional ideas. Okay. So, after the RNNs came and it performed very well, many of the big companies found issue with this approach simply because it took a long time to train. Okay. So, they found that because of the sequential nature, often nowadays they use 25-30 days, but when you started using RNN it will take 2-3 months to train. Okay. Remember, one experiment with so much data is going to take 2-3 months. So, you fire off the experiment and then you will say, okay, after 2-3 months I will come and find out what happened to that output. Okay. So, that's even today we are talking about, even in when we deal with small data, because we have smaller number of GPUs, our students have to wait for 10 days or 14 days or 2 weeks or something to actually get some output, and then see, hopefully there is no bug, and interpret our research results. So, we want to parallelize this. Okay. And so, one of the ways we can parallelize is by using convolutional neural networks, right. Why? Because if you look at convolutional neural networks, you are feeding it with some filter, but that filter is going to operate on all of them. It is going to move along the image in the x and y direction, or if you are looking at 1D, it is going to move along time, right, usually along channels only. So, it is the same filter. So, it can keep first 3, next 3, next 3, that I can easily code. Take the first 3 and multiply by this next 3, because I already have the input, the channel time versus frequency, and I also know what filter I am trying to do in the forward pass. I can parallelly do it. I do not have to wait for the first guide to be done, because that output is not going to influence my this after I move some time steps and do it, and then some strides and do it. Layer to layer, yes, I need to wait, right, because I need to get the output of the first layer before I can process the output of the next layer. So, layer to layer I have to wait, but within a layer I can parallelly move, right. So, the only problem with convolutional neural nets is that I need to have large number of layers to extend the context. RNNs can look at long context, right, with the help of LSTMs and all this. Otherwise there was a vanishing gradient and all this thing, and also it tries to forget when you move along the regular RNN, but with the LSTM and grooves and all these things, we can sort of preserve what are important information. Okay. So RNNs can preserve the history quite well. For me to capture a large context and look for me to look at this guy versus this guy, I need to go, the context has to build. Remember, when I go up the layers in the C and N, even though I started 3, then again 3, then again 3, by the time I go here, I will get at least coverage of about 7, 8 steps in time. Okay. So at this point, I am already covering something from x1 to x6, right. So the coverage is improving as I go up the context or the layers, and the beauty is that I can parallelize this. So people thought, why not use convolutional ideas for instead of encoder decoder, use a collection of convolutional layers to achieve this objective. Okay. But that was sort of there, but quickly another idea came, which is transformers. So that is why the convolutional sequence actually was an intermediate thing, but it never is mentioned because the transformer quickly came after that. So two ideas are going to be happening in transformers. We are going to parallelize things, okay, and so we are not going to do sequential. Secondly, what we are going to worry about is what is the other so is that what was the other thing. So yeah, the parallelization. So what is the other big the other thing is, we are talking about feature maps, right. So different filters capturing different aspects, that is captured by this concept of attention heads. Okay. So we will talk about now transformers. Okay. So let me go and talk a little bit about transformers. So this is what is a transformer. I will go, I mean, don't get scared. So there is going to be, as usual, an encoder block, okay, like in a transformer before we did for RNNs also. So nowadays we always worry about encoder decoder framework. So there is an encoder here, and then there is a decoder here. Okay. So there are, as usual, encoder and decoder. Those two are going to be connected by this attention mechanism. Okay. So there is always going to be an attention mechanism. Okay. Now the problem, and there can be multiple such layers in the encoder and multiple such layers in the decoder. You typically, the encoder till now, whatever you have observed, was a recurrent neural network encoder, and that also could be multiple layers. And similarly, there could be multiple layers of the decoder in the recurrent neural network. Now, in both the encoder and decoder, it had to go sequentially because it had to finish the first guy's job before going to second word and third word and so on. And the decoder by nature is dependent on the previous words, and so there is a sequential approach. Now, how do, and then intermediate, we said the convolutional guys try to parallelize this thing, right. So now we are going to see what is this what is this transformer and how does it achieve this parallelization. Okay. So if you look at inputs, so let us say each column is an input. Okay. Now we want to parallelize this input to go through the encoder. So let us first look at the encoder part, and same thing we can talk about decoder later. So here I am going to give multiple inputs. It could be a sequence of words, so therefore there will be a sequence of word embeddings, right. So how are we going to, what are we going to do with this guy, right. So this is a sequence of word embeddings, okay, and this is the first word. The first column is the first word, second column is the second word, third column is the third word, and fourth column is fourth word, and so on. In a typical RNN, the first column, which is the first word embedding, it will go through a recurrent hidden layer, and then the output of that will be fed as an input here, right. So why are we doing this? Because we want it to capture the history. So the second guy should be influenced by the first guy, the third guy will be influenced by the first guy, and the second guy. Now, instead of depending on a recurrent neural network as a feedback that is coming from the output of the hidden layer, the objective is slightly changed in the in the transformer. So now it is going to say, I am going to, if you take at this guy, okay, because at the input I know the entire sentence, I will come to why I can look at the future also, because if I look at this guy, let me see how similar, or let me take a weighted combination of all the other vectors. So in a recurrent neural network, we were capturing the information from the output, feeding it back as input, output feeding it back as input, and that's how we are capturing the history. Okay. Now in the recurrent, it was, if you go in one direction, it's only looking at the past history, or if you're looking only from the future. Now in transformer, they said, I mean, in the most general case, and we will see how we apply it for translation law. Most general case, given that I am at a particular point, let me take all the knowledge that I have before and after, both the past and the future. Okay. How do we do it in practice? Let us worry about it later. Okay. So if I am looking at this particular time instant, right, this particular word, I am looking at all words that occurred before it and all words that occurred after it, and I am going to find some relationship between these words. So in a recurrent neural network, I was feeding the output from the previous guy as an input, and using these two, we are somehow hoping the network will learn. Now I am going to say it's the same thing, but I am going to look at all words. Why only words that occurred before or words that occurred after? I will look at all words, and I am going to measure some kind of similarity between these words to help me know which words are more important for my particular word. So if I am looking at this word, this could be the Assamese, right. I am going to look at what are the previous and the future words and see what is the correlation, how similar they are, and if some words are going to be very important in the future or in the past, I am going to give a lot of weightage to it. Okay. So how am I going to do this? So this is going to be done by using this idea of queries, keys and values. Okay. So what does that mean? Basically, we are going to look at something called inner products. Okay. So which is basically nothing but similarity in terms of cosines, right. So what do I mean by that? Okay. So just to make my point a little more clearer, right. So if I look at two vectors, right. So let us say this is a vector x1 and this is a vector x2, or if you have looked in high school, if you had two vectors a and b, right. So this could be the vector a and this could be the vector b, right. Now how do I find the angle between these two vectors? Okay. So if you look at this said that cos theta, the angle between these two vectors, is nothing but the inner product. This is called the inner product or dot product divided by whatever the norm of A and the norm of B, right. This is the way you would have written it in high school. Okay. So basically, if two vectors are similar, then what if theta is 0, right, that means A is like this and B is also in the same direction. That is what it is saying, right. And basically you are normalizing it by the vector length. So what you are looking at is, are they looking in the same direction, just maybe they are scaled versions of each other, or are they, so this is the one case, and we say theta equals 90 degrees, then A and B are completely in orthogonal directions. So B has very little information in the direction of A, right. So if I project it, it has very little information in the direction of B, has very little information in the direction of A, or A has very little information in the direction of B, right. So therefore they are not very informative, whereas if theta is 0, then they are highly informative, that is that A and B are highly correlated. So they are all in the same direction, except for some scaling they are very similar, right. So this concept of inner product is important, right. So what is this? What do you mean by A dot B, right? So if you remember, if A is a vector, let us say A11, A12, A13, and B is the vector B11, B12, B13, right? It should actually be column, row and column. So okay, so 2 1, 3 1. I am just writing it properly. Okay, so okay, so B is B11, B21, B31. Then the inner product A dot B is nothing but A11 multiplied by B11 plus A21 multiplied by B21 plus A31 multiplied by B31. Okay. So, this is what we mean by inner product, right. So, this is how we define it, correct. So, also sometimes we write it as A transpose B, right. So, that is the definition for vectors, right. So, that is how we write it, right. So, the same idea we are going to see. So, here in our, let us say there is one word, the, right, or how are you. So, these are your word embeddings, right. So, this is your input. Now, these are vectors, right. So, I can call this as some vector E1, this vector is E2, this, or let me call this as V1, V2, V3. Okay. So, let us say this is a vector V1, this is a vector V2, this is a vector V3. Okay. So, now you also want to see how similar V1 and V2 are. So, what will you do? You want to take the inner product of V1 with V2 and V1 with V3, and this is showing some similarity for the first vector with respect to the second vector. This is the similarity of the first vector with the third vector. That is what you are trying to measure, right. So, that is what you are doing. So, this idea is all that is there. So, similarly, if I want to measure the similarity of second vector with the first vector, right, then I will write it as alpha 2 1, and second vector with the third vector is alpha 3 1, right. So, now you see it is sort of the first vector versus second vector versus first vector, sorry, this should be alpha 2 3, second vector with third vector, right. So, that is how we are going to sort of find the similarity. Remember, if it is close to 0, that means the angle is close to 0, cos of 0 is close to be 1. So, higher the values, so here cos theta is going to be close to 1, right. So, it is approximately 1, that means they are highly similar. Here cos 90, therefore, it is almost going to be 0, that is they are not very similar, right. That is the whole idea we are going to be talking about, right. So, that is the basic idea that we are going to look at inner products as a way of measuring similarity. So, to do this operation, so this is the actual vector, they are going to call, so that we are not confused, but you may get confused, they are going to say something is query and something is key. Okay. So, key is basically, am I looking at first guy with respect to other guys. So, I will call that as a query and a key. So, it will be the same vectors again fed here, okay, but now we are going to call them as query and key to find out the similarity between them, okay, and these vectors continue to be our usual feature vectors or embeddings or word embeddings, but the similarity between them, instead of calling this V1 and V2, V1 and V3, we will use the concept of query and key, that one of them will be called the query, the other is the key, and using that we are going to find the similarity. So, if I made this clear to you, query and key are also coming from the same vectors only, okay. We are only calling them by a different name, I mean from database, queries and all this, we have borrowed from some ideas from there, and we are using it to distinguish from the actual guys, okay. So, what do I do, right? So, for example, okay, so let me look at this guy, okay. So, actually as I said, I am going to take, these are your word one, how are you, the different word embeddings. From that, actually we will multiply by some embedding matrices or query matrices. I am not, that will confuse you, so do not worry about these matrices. We are again going to create something called values, keys and queries. What does that mean? So, let me take the specific example of the tth vector, right, tth word. Now, the tth word I want to see, already I have a embedding for the tth word. Okay. So, let us call that as v of t, that is the embedding that is already here. So, that will actually, if you ignore these matrices, this guy will get copied as it is. So, let us say my tth word embedding for the tth word is v of t. Okay. Now, I am going to, that also becomes my query. So, this v of t is also going to be v of t here, right, which I am going to be using for all of the other sentence, other words. So, if I am looking at the fifth word, so I want to find out the similarity of the fifth word with the first word. So, the first word, we know the word embedding. Now, we are going to purposely call to help us easily distinguish. This becomes my key. So, the first word key, K1, is also the word embedding for the first word. Remember that Qt is a query for the fifth word. So, the query for the fifth word is same. I am now looking at the fifth word. Let us say t equal to 5. So, now I want to see how the first word is looking similar to other words, and I am going to adjust the fifth word a little bit. Okay. So, the query is basically going to be t right now, which is because my interest is in the fifth word, but my key is how is it similar to the first word, to the tth word itself, the fifth word itself, or the capital T. Let us say there are 10 words, the 10th word, right. So, for each one of them, I am going to compute the dot product, which is nothing but the transpose or the inner product or whatever you prefer, right. So, both the query and the key are coming from our embeddings only, okay, but you are giving them special names. Actually, they are not same because of this matters, but for understanding purpose, do not worry about it. Okay. So, I am seeing how the fifth word or tth word is similar to the first word, similar to the 10th word. Let us say there are 10 words in this sentence. Okay. So, how do I find out? So, I take that tth word, which is the fifth word, call that as a query now. I look at the first word embedding, which is the query, and K1. I take the inner product. We have seen what the inner product is, like a transpose operation. You will get a number, right. So, that number is alpha T1. Why is this T and 1 coming? T to tell me that it is the fifth word that I am right now interested in, and 1 is because I am measuring the similarity with respect to the first word. Similarly, alpha TT means the tth word similarity with itself. Okay. Alpha T, capital T means the tth word with the last word, the capital T word or 10th word. Okay. So, these are some numbers. Again, because these are numbers and I want to give some probabilistic kind of thing, I am going to give it like a softmax so that they all add up to 1. Okay. So, now after doing that, the T1 will become beta T1, beta TT and beta TT. The reason is when I add up all of these numbers, they will add up to 1. It will give me a probabilistic kind of thing, so that the total weight will add up to 1. So, I am adjusting or normalizing the weight, not because I want to give a probabilistic interpretation, but more that the combination, these weights all add up to 1. So, when I add up, it does not become some big numbers, right. So, the weights are all going to add up to 1. Okay. Now, what am I doing? Actually, my interest is in finding out the tth word, but the tth word is going to be influenced now by the first word, which is V1, multiplied by the similarity between the first word, which is, and the tth word. So, V1 itself I am going to take some weighted combination, Vt with some combination, and V 10th word or V capital T with its own weight. So, essentially this OT now is not, is going to be slightly corrupted or perturbed version of the original VT, the word itself, by the influence of all of these guys. This is called attention, self-attention, because each guy is attending to all other guys and finding out how similar it is and adjusting itself. Okay. So, there is some sort of similarity between this and what we did for word to vec. Okay. Why is that? In word to vec we took those sentences and remember we created average of those guys, and that told me the word embedding. Okay, so there is a lot of similarity. So let me help you understand. As I said, if you understand word to vec, this attention is going to be a very similar kind of concept. Okay, so let me just explain to you what is happening, and that will give you some similarity between the guys. So if you remember, in word to vec, I had the cute dog, right? So that is now my prediction word. So dog was coming somewhere here. Dog jumped over. Okay. So here these were vectors, one hot vectors, which got multiplied by the embedding matrix, this embedding matrix, this embedding matrix, and we created an embedding matrix that we thought will be a good idea for predicting the dog, right. So from this I expand back with a W matrix and and a softmax to correctly predict this. So this with the context the, cute and jumped over, we got an embedding matrix that helped me predict dog better. If you look at this slide, remember this was the, cute. Let's say we are trying to predict the dog. Here I have taken for 5 words context, so it can be 2 left and 3 right. Then we fed through the embedding matrix. You will get 5 guys coming. We are going to take an average kind of thing, right. So this is what I mean by average. I am giving equal weight to all of these vectors, right, which are giving the left and the right context, right. So the same idea, but now we are going to learn that weighting in a better way. Okay, we are going to say that that is a quantity that I will like to learn, and how do I find the those weights? Those weights are going to be predicted by the inner product, the how similar the two words are. Okay, in some by the cosine distance idea. So if you remember here, I am taking an average word embedding, right, instead of, and we had this missing word itself. Now I am going to give the missing word also as one of the as the word itself. So there is no concept of trying to predict. So if you recall, and then next I would do the prediction part, right. So after the average vector came, I will go through that reconstruction and then softmax and get the dog vector here, right, and by using softmax and so on, right. So here we are not going to do that. It's inspired similar to that idea, but we are not doing exactly that. Okay, so we are sort of doing it, but not exactly that. Okay, so here what is happening is, there we would have taken the beta ones would have been all equal, right. If they are 10, then 1/10 we would have taken and just added all of the vectors, right. But now I am not doing that, right. I am going to find the context depending on how much weight or similarity it is giving, right. So each word is going to give different weight depending on how similar it is to the word of interest. Let us say the dog was a word of interest. I am going to look at the 2 left and the 3 right and itself also, and take a weighted combination of them. Okay. So that is the basic idea of self attention, and somehow that does remarkably well. Okay, and we will see the one special case of this is called BERT, right, and that BERT and word to vec are very similar. Okay, there is only a small difference, but BERT has made a big impact in NLP. Word to vec did a big jump, but BERT did even more important things, even more dramatic improvements. And so BERT is also coming from the same transformer idea, except that it is only going to use the encoder. Okay, so very simple. So it looks very confusing. I have simplified it to as much extent as possible. The whole idea is, if I am looking at a particular word embedding, right, I am going to take that word embedding. I could continue, or say like the dog, try to see what is it that is influencing me. So I look at the left words and the right words. How do I find the influence of the left words and right words? let us say I am interested now in the tth word, right, let us say fifth word or fourth word. So, that becomes sorry, fourth word, that becomes my query, right, these guys. Sorry, I should have lighted it up. I am interested in the fourth word, and so that becomes my query. I am always going to carry that, and I am asking how is that fourth word similar to the first word. So, now my key is actually copying the first word, embedding and calling it as key. Okay. So, the key is nothing but the first word embedding, the query is the fourth word embedding. I am looking at the inner product or dot product between the two, the A transpose B by cos theta of that. So, that will be some value A alpha T1. Similarly, for the tth word itself, I can look at it, and similarly for the fifth word with respect to the 10th word, now the query key will become the 10th word. So, I am looking at the similarity, but now these similarities are not normalized, they will be some numbers. I make sure that they lie between 0 to 1 and add up to 1, and then I am taking that, this is weight now. I am taking the first words embedding itself there in the word to vec. I just took the average of all of them. Average means what? Take equal weights for all of them. So, all of them will be, if there are 10 words, 1 by 10, if there are 15 words, 1 by 15, if there are 4, 1 by 4. We are not doing that. We have learnt it more intelligently here and taking a weighted combination and also the word itself. Now, I am not doing prediction, I am trying to adjust the word embedding of that particular word. How can I adjust it a little bit based on the context, okay? And that therefore, this is not only the word as it is progressing, it is now adjusting itself depending on the context in which it occurs. What were the left words, how much influence does it have, what are the right words or how much influence. If they are not influencing, it will be almost unadjusted. If it is influencing, it will change to a larger extent. This is called self attention, which is a very, very important concept, okay? And that is the basis of transformers, BERT, all of the things that we do, okay. So, I will stop here and I will continue next class with the actual transformers. This is the building block for the transformer, okay. So, thank you, I will stop here.